In today's lesson, we're going to talk about rational functions. Before we actually break down our vertical asymptotes, let me remind you that we actually know a parent function that fits this category. That is our reciprocal function. That 1 over x belongs in this category. So if you kind of keep in mind, it looks kind of like 1 over x. That's what most of these look like. That will help you as we go through this process. First, let's focus on this little box here, the vertical asymptote. Now, a vertical asymptote is going to occur at some x value a. In this case, I chose the x value a is very common. And basically, you are going to think about as we approach a, then x value of a from the left. That's this notation. That is a calculus notation that we're preparing you for. So this is x is approaching a from the left. Our function will either increase or decrease without bound, meaning it will approach positive or negative infinity. So let's think about our reciprocal function. As we approach 0 without bound, from the left-hand side, you see how it is going downward to negative infinity. That's all that means. That's what that shortcut means. Okay, so let's go back and let me show you again what it says. This is notation. We are coming in toward A from the left. We are going to either go swoop up to positive infinity as we approach that asymptote or down. You skim across that asymptote. This notation means I'm coming in from the right side. And it says as we approach A from the right, our function again will increase or decrease without bound. We want to find a vertical asymptote by setting the simplified denominator equal to 0. Now, what do I mean by simplified denominator? Remember in our 6.0 investigation, the first thing we did was kind of reduce those fractions. I'm talking about the reduced fraction form, okay? So a vertical asymptote is a spot in a graph where there is what's called an infinite discontinuity, an infinite break, an infinite where we're going to swoop up or down toward infinity. Now, our parent function, 1 over x to the n, so that would definitely be the one we already know. Our reciprocal function falls in this category. The power is odd. We'll have a vertical asymptote at 0 and a horizontal asymptote as 0. Okay. What's great about these ones is as we approach 0 from the left, if our power is odd, like our original here, so it's this category, we already know what it looks like. As we approach 0 from the left, we're going down. As we approach 0 from the right, we're going up. So we kind of know what it happens if it's an odd power. And that's because our odd power is our 1 over x. So let's put it there actually. But let's talk about what happens when it's an even power. So the actual one I graphed, when I graphed this on Desmos, there was a squared on that. So 1 over x squared, 1 over x to the 4th, 1 over x to the 8th, whatever. In that case, if our power is even, as we approach 0 from either the left side or the right side, we are always going to go in the same direction. Because think about if you square a negative, what happens to it? It goes positive. If you square a positive, what happens to it? It's positive. So that's why that happens with an even power versus an odd power. Positive stay positive for an odd power. Negative stay negative for an odd power. So the positive side goes to the positive. The negative side goes to the negative. But as soon as you make that power even, the positives go up, the negatives go up. And that's why that happens. Okay. But they all have horizontal asymptotes at 0 if they're in this form. Okay. Now let's talk about some of the language you're going to be hearing as you go through this lesson. A rational function has a polynomial in its numerator and a polynomial in its denominator. It's important that we look at the lead term of our numerator. We're going to call the degree of that n. It's important that we know how to find the lead term of our denominator. We're going to call the degree of that n. Now, why is it important to have that n and m? Well, that is going to help us find a horizontal asymptote. Now, if our parent function is 1 over, we can just use the even odd we saw in the box above. But the problem is we could have a polynomial, x squared plus 2x minus 7 on the top, x cubed plus 7x minus 2 on the bottom. So if we happen to have something that doesn't fit the categories here, if we just have a rational function where the degree on top is n and the degree on the bottom is n, let's talk about how to find the horizontal asymptote. If the degree on the bottom is more than the top, so m is bigger than n, then it becomes exactly like the functions we saw up above. If the degree on the bottom is more than the degree on the top, then we always have a horizontal asymptote of 0. We don't have to think about it. If the degree on the bottom is more, we always have an asymptote, a horizontal asymptote at y equals 0. So horizontal asymptotes, you might recall, this is our ends. What are happening on the ends? Well, if our higher power is in the bottom, our ends are always going to head to 0. If the highest power is on the bottom, our ends are always heading to 0. And we saw that because the only power, hence the higher power, is in the bottom. And where did our ends head? We're talking about this end and this end, this end and this end. What did they always head toward? 0. So that is something, the left end and right end behavior of a rational function whose degree in our denominator is more always heads to 0. You just have to know that. You just have to memorize that rule, okay? If they match, this is kind of the weird one. Let's say we have a lead term of x to the 4th on the top and an x to the 4th on the bottom. What is happening as you plug in very super big numbers, the x to the 4th start acting so similar that we just use our coefficients on those lead terms. See how there was an a on our lead term from the top and the b was our lead term on the bottom. Just use those coefficients. So the ends will always head to a over b. Again, just a rule you have to memorize. And as we go through the process, I'll show you an example of each so then you can kind of see how to clarify. If the top is bigger, there is no horizontal asymptote because the ends act like a polynomial. They're going to go up or down, positive infinity, negative infinity. So they kind of act like the same rules for polynomials. And then the last thing here is a hole in the graph. A hole in the graph occurs where a factor in the top and the factor in the bottom are a match. Just set that factor equal to 0 and you'll find a hole. Some other little piece I want to add before we move on from this, that the domain of a rational function you're going to remove any holes and vertical asymptotes. You're going to remove any holes or vertical asymptotes. So factored form is going to help us for all of this stuff. That's why we practice it. I don't take things lightly when it comes to trying to prepare you for what's to come. So when we looked at things, I believe it was maybe Monday, I think. Maybe it was Tuesday. But when we looked at how to reduce those functions, I was trying to prepare you for what's to come. So you should always try to get things in factored form, because the domain of a rational function uh, is just going to be found by removing any holes and vertical asymptotes. That factors um, uh, that factored form is going to help us factor the top and bottom. The bottom really is where we know it can't equal 0. So that's some of your rules. So I'm going to let it there for a minute. Let's make sure everybody has all the rules they need written down. And then we're going to look at some examples. And then we're going to do a little bit of iMath together. Now, one of the things I will remind you of, you were sitting in a college level class, whether you're getting high school credit or college credit, doesn't matter. This is a college level math class. It requires that you actually spend a little bit of time studying the new terminology. Make sure you're looking at what these words mean. What is it telling us? If they ask for a horizontal asymptote, what does it mean? If you don't know the rules, you're not going to be as successful as you make sure you understand the language of it. It's like almost math kind of has its own language. So, it's like any foreign language. If you don't understand the terminology, how are you going to answer the question? So please be very careful with that. Okay, that being said, yes. Yeah. So as soon as everyone's ready, we'll look at the examples that are down below.
All electrical tech students attend. Wheelchair, please report to the electrical classroom at this time. Thank you.
Okay, are we good? Okay, so now let's look at some examples. It says f of x equals 5 over x represents the ratio of the volume of flavoring to water in a large vat to produce a mixed drink. Fill in the table about this function. So this is just saying that volume in the tank is that common ratio of 5. Don't worry about that. What we need to worry about is if we plug in these x values, what is our f of x going to give us? So then we have some points to plot. Okay. So if we take 5 over 1/2, remember 5 over 1/2 is the same as 5 times 2 over 1, because it's going to divide by a fraction is the same as multiplying by its reciprocal. So we're just really multiplying by 2. So the answer is 10. 5 divided by 1 is 5. 5 divided by 3, I don't know, 5/3. 5/3 is about 1.7 rounded to a nearest 10. 5 divided by 10 is 1/2. 5 divided by 500 is 1 over 100. 1 over 100 for decimal purposes is 0.01. 5 over 2,000 is the same as 1 over 400. Super small decimal, even closer to 1. It's 0.0025. Now, let's think about our parent function. If our function is 5 over x, our parent is 1 over x. All the 5 did was stretch it a little. So normally our parent function is at 1, 1. If you plug in 1, you get 5. So it just kind of stretched it. We still have an undefined value, a vertical asymptote at x equals 0. The ends, because our denominator, has the higher power, we still have a horizontal asymptote at 0. So it's just something you have to recognize what that graph is. Now, when I graph a rational function, so I'm going to make my graph paper a little clear here. So if you want to add in your x and y axis for me. The first thing I always try to add to any graph paper related to a rational function is I put on the asymptotes. So we know 0 is undefined. Put a dashed line at x equals 0. I know the end behavior, the left end and the right end head to 0. Put a dashed line on our y-axis. Now, this is a real-life application. There is no negative portion of this graph in real life. We can't have a negative number. We're not going to assume we spilled it all on the ground, but let's actually plot the points. At 1, we were at 5. If you plugged in 2, you're at 2.5. We did plug in 3, and we got about 1.7. We did plug in 10. We got 1/2. The left side, as we approach 0 on the left side, we are getting closer and closer to infinity, and our height is getting closer and closer to infinity. As we approach or plug in larger and larger numbers, we're getting closer and closer to a value of 0. So we would say, as we approach 0 from the right, we are heading to a height of infinity. So we could say, as we approach 0 from the right, think of the positive side of 0 to the right of 0. Our y is heading to positive infinity. Now, that is the real life values of this graph. But for math purposes, I do want to plug in negatives. Again, the negative portion isn't really in the domain of a real life problem like this. But if you plug in -1, we would be at -5. If we plug in -2, we'd be at -2.5. If we plug it in -3, we'd be at -1.7. If we plugged in -10, we'd be at -1 1/2. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, -1/2. There is a mirror on this side. So we could say, as we approach 0 from the left, we are heading to -infinity. So that's what the graph looks like. Now, let's talk about the end behavior. The end behavior, let's put in the correct notation for that, because I believe that maybe iMath uses some of that correct notation. As our x is heading to the right, remember that's always infinity. As x is heading to the right, our y value heads to 0. As our x is heading to the right, infinity, our y is heading to 0. As x heads to the left, -infinity, our y, our height, is heading to 0 again. This is what is your horizontal asymptotes doing? That is the correct notation for that. This is what our vertical asymptote is doing. That is the correct notation for that. And that's preparing you for that notation that you would see in a calculus class. They use a few other little pieces and parts, but it's very similar notation if you ever take calculus. Okay, So we have to know how these graphs look. We are going to explore more and more complicated versions. So that's what we're heading toward as we go to up to 6-3. We will be having lessons up to 6-3, and you'll have a 6-3 lesson probably when you are that week after Thanksgiving break, that virtual lesson. There'll probably be a video and a worksheet to go with it, or maybe an iMath assignment. But that's where we're heading. We want to get at the most complicated type of graphs. Okay. So in this particular examples, we're going to find the vertical asymptotes, the horizontal asymptotes, the holes in domain. Now I'm going to give you kind of a structure of what you want to do each time, and we'll follow that same pattern, so then the pattern hopefully can get melt in your little brains, or big brains, however you want. Okay, so let's talk about the rules. The first thing we want to find is the factored form. Now, problem 2a, it's in factored form. You check, done. We don't have to factor, it's done for us. Okay. Second thing is we're going to find the holes. The holes occur at a common factor on top and bottom. So we're looking for common factors. Well, there are none. This one doesn't have a hole in it. It doesn't have like an x plus 7 on top and an x plus 7 on the bottom. There's no hole in this graph. Third thing you're going to find is the vertical asymptote. Once it is in factored form and you have taken out the holes, the remaining factors are going to give you the vertical asymptote. It's an easy thing to find. It is where the remaining factors of the bottom, so the reduced bottom, is equal to 0. So that's easy to find. X plus 4 equals 0. At -4, we have a vertical asymptote of -4. Great. Now think about this function. We know how to graph this function. We know 1 over x is that reciprocal function. So 1 over x plus 4 has just moved it to the left 4. So we should expect the vertical asymptote has moved to the left 4. So it makes sense. Those things should go together. That leads us to our domain. If you found a hole, if you found a vertical asymptote, take it out. So that's why I always do factor it, take out the holes, take out the vertical asymptotes. Now you get to list the domain very easily. The only value I skipped was -4. That's the only value I skip on the graph. So I go from -infinity up to -4. I skip it. I keep on going. That's my domain. I've skipped. The only value I skip in this graph is -4. There's a piece to the left of -4. There's a piece to the right of -4. That's our answer. And then the only thing I have left to find then on this list is horizontal asymptote. If the power in the bottom is higher than the power in the top, we only have x's in the bottom. So obviously this is a rational function, fits our category of we have higher powers in the bottom, because the lead term on the top is x to the 0. There's no x's. The lead term in the bottom is x to the first. The bottom wins. Then it's always y equals 0. The ends always head to 0. So we're going to do steps 1 through 5 for all of these. Okay, so let's do exactly the same thing now for B. Yes. There will actually physically be in a hole in the graph, will actually be like that. We haven't done them yet as far as what they look like. We're going to find one, I believe, in the next few examples. So I'll show you how to find them first. We'll show you how to graph them coming up. It's coming up. But yeah, it's actually physically just a little physical point that there's like a little hole there, and that it's not a vertical asymptote. So a hole, this weird little line that we skim across, it's just a little hole, jump across. And I'll show you how that appears in a graph when we get there. We just haven't got that far. Yes, what else? No problem. Okay, so now let's go on to part or 2B. 1, factored form. That's done naturally for that problem. There's no way to factor it. It is what it is. 2, there are no factors that match on top and bottom. The factor on top is x. The factor on bottom is x minus 5. They're very different. They're not the same. So that leaves us to vertical asymptotes. The vertical asymptote is where the remaining factor, or in this case, only factor in our bottom is equal to 0. So that's at 5. That leads us to 4. What's our domain? Well, we didn't skip any holes. There's not any holes, like little holes in the ground we got to jump over. But we did skip 5, so our domain has to reflect the fact that everything works but 5. So we're going to go from negative infinity up to 5, then from 5 to infinity. The only value we skip is 5. Now, for the very first time, our horizontal asymptote is different. If we look at the top of this fraction, the lead term on the top is x. The lead term on the bottom is x. When they match, we pull out the coefficients of those things, and that's what the ends head toward. So if we pull out the coefficient on the top is 1, the coefficient on the bottom is 1, our horizontal asymptote is actually at 1. So this graph has a vertical asymptote at 5, has the ends heading to 1. Now, how could we check our work? Well, there's this beautiful, lovely thing. I wish they had it when I was a kid, but I didn't even have a scientific calculator. That tells you how, well, I was kind of a poor kid, but I didn't have a scientific calculator. I remember some of they were very expensive at the time. Like, your TI 30s, now you can go to Walmart and get it for like 10 bucks. Scientific calculators had just come out when I was in high school. Oh goodness, I'm old. And they were very, very expensive. So some of the rich kids had them. I was not a rich kid. Okay, so let's graph our function. If you see x over x minus 5, you can see if you typed in your vertical asymptote, x equals 5. That so is not what I wanted to type. How about I hit the equal to button? X equals 5. See how it skims it? Okay. If you plug in your horizontal asymptote, or what you think the horizontal asymptote is, the ends should head to 1. So look at our graph. Is your graph heading to 1? Yes. Never touches it. Now, horizontal asymptotes are a little weird. Sometimes they can wiggle across it a little bit, but it will always get closer and closer to it at the ends. A vertical asymptote we can never cross. A horizontal asymptote, sometimes there's some wiggle action depending on how complicated the function is. But vertical asymptotes are your kind of like, it's like a force field, a barrier you can't ever cross. But yeah, horizontal asymptotes tend to act like vertical asymptotes too most of the time. They get closer and closer without touching. But it's not quite as a requirement as it is for that vertical asymptote. But you can see, you can check your work in decimals. Okay, let's do another one. Now, see, for the very first time, when I told you to factor it, we have some work to do. So that's why we did what we did in our 6.0 investigation. I wanted to get you ready for this. So let's get this in factored form. Our factorization, there is no factorization on the top. The factorization on the bottom, there actually is one that works. Just put your 2x and x. The factors of 4 that make 9, no. It's the factors of 2 times 4, or 8. 8 is 8 times 1, which adds up to 9. So how can we get the 8 we want? So that means we got to put the 4 here So we get an 8 and a 1 here. So we get 9. You can do slide and divide. There's lots of methods, but that's how that factors. Now, our second thing we still haven't come across, it's coming, but is there a factor in top that's a perfect match for a factor in the bottom? No, so there's none. That is something we should immediately check for. So then that leads us to our vertical asymptotes. There is a vertical asymptote at 2x minus 1 equals 0 and at x minus 4 equals 0. So there's actually 2 for this graph. Our graph actually is going to be broken down into 3 pieces. We have to skip a value of 1/2 and we have to skip a value of 4. So we will look at the graph. I want to show you how it breaks down into multiple pieces because we have to skip 1/2 and we have to skip 4. So put those values in order when doing domain. I have to go up to the 1/2, almost get there, jump across that vertical asymptote, get up to 4, almost get there, and then I get to keep going. So you'll see how we have a skip at 1/2 and a skip at 4. And then that leads us to our horizontal asymptote. The lead term in the top is 3x. The lead term in the bottom is 2x squared. The 2x squared, 1. It's always y equals 0 when the bottom power is the higher one. It's always y equals 0 when the bottom power is the higher one. How can we check our work? Good old Desmos is our friend. So if we plug in 3x minus 4, sorry, I got to put parentheses in. So make sure your whole top is surrounded by parentheses. And then I'm going to put the original, just in case I might have factored wrong. It will help me find it. You'll notice our graph is in 3 pieces. If you type in x equals 4, x equals 1/2, and y equals 0, we can see very clearly that our graph indeed has values. Sorry, I can't get that one to work. Wait, let's see if I can do that. There we go. You can see that our graph is in 3 pieces. Our domain is in 3 pieces. We have a vertical asymptote at 1/2, a vertical asymptote at 4. Our ends are heading to a height of 0. So these graphs, eventually we're going to have to graph that, unfortunately, but all those pieces, a ton about what's happening. Okay. So that is part C. Now let's do a few more. I find that this one needs factored. I'm going to write, I'm going to take out the 2 from this back piece. The only way to factor this one's divisible by 2, so I'm going to take that out. Okay. On the bottom, there is an x I can take out. I can't take out anything else. The only time so far we've seen there is an actual hole. The hole occurs because there is an exact match of an x on top and an x on the bottom. So there's a hole at x equals 0. So then we take that hole out, and for the rest of our problem, we're going to pretend it was never there. Nope, it wasn't there. And then we're going to continue the process with the reduced form. Okay, so let me say that again. We factor so we can find any holes. That's a matching factor in top and bottom. And if we find one, we're going to remove it, and we're never going to speak of it again. Well, there is something we'll do eventually. But okay, that leads us to 3. Vertical asymptotes are what are the remaining factors in the denominator, and how do they equal 0? So it's just where 5x minus 2 equals 0. So add 2 to both sides, divide by 5. So there is a vertical asymptote at 2/5. So what have we skipped? We've skipped 0. We've skipped 2/5. So our domain has to include the fact that we skipped 0 and we skipped 2/5. So go up to that hole, jump across it so you don't fall in the hole. Get to our vertical asymptote, jump across it because we can't touch it. There's a force field there. Okay. So you'll see that we have skipped our whole value of 0 and our vertical asymptote value. And then finally, where is our horizontal asymptote? Well, whether we use the original or the reduced version, I like to use the reduced version. The top, the lead term from the top, I would need a 2 and an x and an x, a 2x squared. The lead term of my bottom has a 5x. If the powers matches, we use their coefficient. Those don't match. If the bottom is more, the ends head to 0. That isn't what happened. The top actually wins. In this case, there's an extra x in the top. So there is none. The ends head to either plus or minus infinity. The ends kind of, I believe the right end would go up and the left end would go down like an x to the first, like a line. And I think this one actually would end up looking pretty linear. As it kind of looks kind of like a, it's a weird graph, but okay. Let's do 2 more of those, and then we're going to jump to iMath. There's not much we can do to factor E, except you might as well take out a 2 just to make sure that we don't have a matching factor in top and bottom. There is no factor in top and bottom that match, so there's no holes. But there are some pieces where we're going to have some vertical asymptotes at 3x minus 4 and x plus 2. So make sure to set those remaining factors, in this case only factors, equal to 0. Solve for x, we got it. So this would be 3x equals 4, so x is 4/3. And this would be x is negative 2. Only once we've found any holes or vertical asymptotes do we move to domain. Now, make sure you're always putting your domain in numerical least to greatest order. So we're going to skip negative 2 and 4/3 in that order. So we're going to go to from negative infinity up to negative 2, skip it, go up to 4/3, skip it, but we can keep going. So if you were to put this graph into Desmos, this graph would be in 3 distinct pieces. There'd be a curve to the left of negative 2, a little curve of some sort between negative 2 and 4/3, and then a curve again from 4/3 to infinity. So we can expect a 3-piece graph, which is weird, but Horizontal asymptote. The lead term on top is 2x. The lead term in the bottom, if you were to multiply 3x and x, is 3x squared. The higher power's in the bottom. It's always going to 0. Very much like our original reciprocal function, that 1 over x function. One more, one more, and then we'll open up iMath and do, there's a pre-class in there for sure. We'll do, you know. So one of the techniques that I've always found help my algebra students is be consistent in the order in which you do things and the pattern of which you do things. Do it yourself too. It will be helpful as you go through problems like this. Okay, let's do F. First thing we put, it is in factored form. There is a 5 factor that we can remove from both the top and the bottom. I'm sorry, from both terms in the top. Our bottom is the difference of squares. So use your square roots. That's x plus 3 and x minus 3. So there's our factor form. Now, we do have a matching factor in the top and the bottom. So this particular graph would have a hole at where x plus 3 equals 0, or at negative 3. So there's a hole in the graph. We'll discuss more what to do about that when we draw graphs. We're not drawing them yet. We're just kind of analyzing the algebra right now. We got to do the algebra first before we can get to the graphical portion. But this has given us so much information. Third thing we do is we use the reduced form for the rest of the problem. Use the reduced form for the rest of the problem. This is a reciprocal function that's moved to the right 3 and stretched a little bit. We should know what this looks like. But it's got a little hole, but don't worry about that. Okay, so our vertical asymptote, set our remaining factor equal to 0. X minus 3 equals 0 at positive 3. So our domain, we have skipped negative 3. We have skipped positive 3. So that is our domain. Last piece, horizontal asymptotes. The lead term on top is 5x. The lead term on the bottom is x squared. The x squared 1. When the x squared, when our denominator has the higher power, that degree is higher, you always go to 0. So turn this in.